Hi, and welcome to my talk. The topic of this session is about a new approach site reliability engineers can use to automate performance tuning of system configurations leveraging machine learning techniques. We will start by discussing the SRE challenges for ensuring application performance and reliability. We will then introduce a new approach based on machine learning techniques, and then we will see how the new approach can be used to automatically tune today's complex applications by focusing on optimizing a microservice application running on Kubernetes and the JVM. Finally, we'll conclude by sharing some takeaways on how this approach benefits SRE teams. Before proceeding, please allow me to introduce myself. My name is Stefano Doni, and my role is CTO at Akamas. Performance engineering has always been my topic of interest and passion. So let's start by discussing why system configuration are so important to the job and mission of SRE. I would like to start by reviewing at the high level what really is the job of SREs. Citing the seminal SRE book by Google, it's no surprise that any SRE deeply cares about service performance, efficiency, and reliability. To understand in practice what does that mean, let's have a look at some of the core tenets. Pursuing maximum change velocity without violating SLOS. This tenet is well known and refers to the goal for SRE to accelerate product innovation and releases while still matching the agreed service level objectives. For example, ensuring request latency stays below a target value. Demand forecasting and capacity planning. SRE should have a clear understanding of what is the capacity of the service in terms of maximum load that the service can support. This is typically achieved via load testing to determine the right amount of resources to provision to the service, for example, before a product is launched. Efficiency and performance. Efficiency means being able to achieve the target load with the required response time using the least amount of resources, which means lower cost. SREs and developers can change service software to improve its efficiency, and here is a major area where configuration can provide big gains, as we are going to see in a moment. So what is the role of system configuration and why are they so important for SREs? System configuration are key for SREs as they can really impact service performance, efficiency, and reliability. Let's consider a real-world example related to a Java service. After a JVM reconfiguration on day 3, the CPU usage of the application server dramatically changed, 75% reduction actually, while the system was still being able to support the same traffic load. So this configuration change translated into significant gains on service efficiency. On the right, you have another example where an optimal configuration significantly improves service resiliency. While the baseline configuration crashed under load, the best configuration supported the target load with much greater stability. So tuning system configuration really matters. And this does not apply only to Java, it also applies to all the infrastructure levels, from databases to Kubernetes containers, middleware, and application servers to any other technology. But how easy it is to do that for today's modern application? Well, not so much, actually the contrary. The problem is that performance optimization is getting harder and harder these days. There are 3 key factors that I would like to highlight here. First of all, the explosion of configuration parameters. Today, a JVM has more than 800 parameters, MySQL database more than 500, and for example, on the public cloud, AWS added more than 100 new EC2 instance types just last year. Second, configuration can have unpredictable changes, unpredictable effects. In this example, allocating less memory to a MongoDB database made it run much faster, which is pretty much the opposite of what we have been doing. Third, release velocity is increasing. So this is well known for SRE. It's worth mentioning that it has negative impact on performance tuning, which is largely a manual task done by experts, and as such, it takes a lot of time. So system configuration can play a big role on service performance and reliability, but optimizing them is a daunting task for SREs, given the increasing complexity of technology and modern delivery processes. This is why we needed a different approach. At Akamas, we have identified 4 key requirements that we believe are required to effectively solve this class of problems. First, the new approach should allow for a full stack optimization, meaning that it has to be able to optimize several different technologies at the same time. For example, the optimization might focus on container parameters and runtime settings like the JVM options at the same time. Second, the new approach should allow a smart exploration of the space of potential configurations. If we consider all the possible values for all the possible parameters, we really have billions of configurations. So a brute force approach is simply not feasible and would not work for this kind of problem. To be effective, a solution needs to be identified in a reasonable time frame at an acceptable cost. Third, the new approach will allow us to align to each specific need, priority, and use case of interest by defining custom optimization goals. For example, in some cases, the SRE might want to reduce your service latency to provide the best possible performance at peak load. In other cases, reducing costs could be the key driver for the optimization without violating service level objectives. And last but not least, the new approach should be fully automated to reduce toil as much as possible and to ensure a reliable process with the fastest convergence to the optimal solution. Then let's focus a little bit more on the smart exploration capability. Machine learning is what makes it possible to implement a system that is both efficient and effective at finding good configurations among the billions possible configurations. To explain this point, let's use the aircraft design metaphor. So in an aircraft design process, you first of all build a simple model of the aircraft, which can be used to study the high-level aircraft behavior. We then move to simulations, which can reveal the aircraft behavior more accurately. And as a final step, you then test the finished aircraft to see if it fully matches your design requirements. Of course, at each step, things become more realistic, but also become more costly. These 3 steps can be compared to different approaches in optimizing system parameters. A first approach is to leverage analytical models, such as queue network models. These models are very cheap, but you cannot model complex scenarios, such as the impact of garbage collector on application performance. A second approach is to leverage simulators, which can predict system performance in an accurate way. Unfortunately, those models are quite expensive because they require big data set to be collected, and that cannot be used for different systems. The third approach is to run experiments and change the configuration on the real system. Of course, a brute force approach would be too costly and would not deliver the result in a reasonable time, so we needed to minimize the number of experiments. However, accuracy will be the best, as you can actually measure the effect of parameters on your specific system performance metrics. This is why we advocate for an experimental-based approach for optimizing system configurations. And machine learning provides great techniques and help searching for the optimal configuration in a time and cost-efficient way. While there are several machine learning techniques that can be used, the one which we have implemented at Akamas is called reinforcement learning, as being specifically effective. The key concept of reinforcement learning is that a thinking agent can learn in a trial and error fashion, using the feedback from its action and experiences. Let's now see how reinforcement learning works in practice. This figure shows the 5 phases of the automated optimization process. So the first step is to apply a configuration to the target system of the optimization. This can be a new JVM option, a Kubernetes container resource setting, etc. This step is called an action in reinforcement learning terms. The second step is to apply a workup at the target system so as to assess the impact of the applied configuration. We typically do that by integrating with load testing tools. The third step is to collect key performance indicators related to the target system. It is information, data, and metrics about the behavior of the system under the workload. The fourth step is to score the configuration against the specific goal by leveraging the collected KPIs. The goal could be efficiency of the system, for example. This step is where we feed back the system performance metrics back to the machine learning agent. And this is the so-called reward in the reinforcement learning literature. And it is called by reinforcement learning to understand if the configuration made the performance better or worse. The last step is where reinforcement learning kicks in by taking the score of the tested configuration, that is the reward, as input, and by producing as output the most promising configuration to be tested in the next iteration of the same process. In a relatively short amount of time, the machine learning algorithms layer the dependency between the configuration and the system behavior, thus identifying better and better configurations. An important aspect is what is the role of SRE in this new AI-driven performance optimization process. So SRE still has a key role in the new automated performance tuning process, as it defines the optimization goals and constraints, and then lets the machine learning-based optimization to automatically identify the optimal configuration. Let's see how this new approach applies to a real-world example where we will automate the optimization of a service by tuning Kubernetes and the JVM. In our optimization example, the target system is Google Online Boutique, a cloud-native application running on Kubernetes made of 10 microservices. This application features a modern software stack with services written in Golang, Node.js, Java, and Python. It also includes a load generator based on Locust, which generates realistic traffic to test the application. We will leverage this application to illustrate two different but related use cases. The first use case is related to tuning Kubernetes CPU and memory limits that define how many resources to assign to a Kubernetes container to ensure application performance and at the same time cluster efficiency and stability. For an SRE, the challenge is represented by the need to ensure that the overall service will sustain the target load, while also matching the defined service level objectives on response time and error rates. Service efficiency is also very important in this case, as we want to minimize the overall cost of the service. So we don't want to assign more resources that are needed. Also, as an SRE, we want to keep operational toil minimal and to stay aligned to the delivery milestones. So this is the overall service architecture. The parameters that we are optimizing in this example are the CPU and memory limits of each microservice. These parameters are applied via the Kubernetes APIs. In order to assess the performance of the overall application with respect to different sizes of the containers, we leverage a built-in Locust load injectors. We then leverage Prometheus and the Istio service mesh, respectively, to gather pod resource consumption and service level metrics. The whole optimization process is automated. So what is the goal of this optimization? In our example, we aim at increasing the efficiency of the online boutique application, that is to both increase the service throughput and decrease the cloud cost. At the same time, we want our service to always meet its reliability targets, which are expressed as latency and error rates, SLOs. Therefore, our optimization goal is to maximize the ratio between service throughput and the overall service cost. The service throughput is measured by Istio at the front-end layer, where all the user's traffic is processed. The service cost is the cloud cost we will pay to run the application on the cloud, considering the CPU and memory resources allocated to each microservice. In this example, we use the pricing of AWS Fargate, which is a serverless Kubernetes offering by AWS, which charges $29 per month for each CPU requested and about $3 per month for each gigabyte of memory. The machine learning algorithm we have implemented at Akamas also allows us to set constraints to which configuration are acceptable. In this case, we state that configuration should have a maximum 90th percentile latency of 500 milliseconds and an error rate lower than 2%. That is it. At this point, the machine learning-based optimization can run automatically while we are relaxing or doing some other important stuff. Let's see what result we got. In this chart, each dot represents the cost efficiency of the application, which is again the service throughput divided by the cloud cost, as a result of different configuration of the microservices, CPU, and memory limits as chosen by the machine learning optimizer. The result of the machine learning-based optimization approach is quite astonishing. A configuration improving the cost efficiency by 77% was automatically identified in about 24 hours. The baseline configuration, which corresponds to the initial sizing of the microservices, has a cost efficiency of 0.29 transactions per second per dollar per month, while the best configuration and machine learning found by tuning microservices resources achieved 0.52 transactions per second per dollar per month. This chart also helps understanding how our machine learning-based optimization works by learning from each tested configuration to quickly convert to the optimal configuration. At this point, I guess you may want to know what is the best configuration look like. Let's inspect the best configuration by focusing on 10 most impacting parameters. It's interesting to notice how our machine learning-based optimization reduced CPU limits for many microservices. This is clearly a winning move from a cost perspective. However, it also automatically learned that two particular microservices, the product catalog and the recommendation, were under provision, thus increased both their assigned CPU and memory. All these changes at the microservice level were critical to achieve our optimization goals that we set on the overall service, which is to maximize the throughput and lower cost, while still matching the SLOs. Let's now see how the overall service performance changes when the best configuration is applied. The chart on the left shows how the baseline and the best configuration compare in terms of the overall service throughput. Interestingly, besides being much more cost efficient, the best configuration also improved throughput by 19%. On the right, we are comparing the service 90th percentile response time. The best configuration cut the latency peak by 60% and made the service latency much more stable. Let's now consider another use case for the same target system. Here, the SRE challenge is auto-tune the JVM options of the critical microservice so as to ensure the required service can support a higher target load that is expected, while still matching the defined SLOs on the service response time. The container size is not changed here as we don't want to increase cost. Again, we want to keep operational toil to the minimum and be quick to stay aligned to product launch milestones. As mentioned, the target architecture is the same. With respect to the previous picture, here we are emphasizing the specific JVM options, about 32, that are taken into account, and the specific microservice, the add service, which is a Java-based service that is being targeted by this optimization. Let's see how the optimization goal and constraint are defined in this case. The goal for this use case is to increase the number of successful transactions processed by the AD microservice, the advertisement microservice. The SLO for this service is the average response time, which should be kept no higher than 100 milliseconds. So let's see the results machine learning achieved for this optimization. This chart shows the service throughput and response time under increasing level of load during a load test. First of all, consider the blue and green line representing the microservice throughput and response time for the baseline configuration. As you can see, the baseline configuration reaches 74 transactions per second before violating the 100 milliseconds low on response time. Let's now look at the best configuration. The throughput, which is the black line, reaches 95 transactions per second before violating the response time SLO. Therefore, the best configuration identified by the ML part optimization provides a 28% increase in transactions per second, while also meeting the defined SLOs on response times. So what makes this configuration so good? So the maximum memory was increased, so actually a 250% increase. Also, the machine learning learned to optimize the garbage collection time, which is a common question many JVM developers and Java developers has. So in this case, machine learning understood that it was best to change the garbage collection from G1 to parallel. It also decreased the number of garbage collection threads from 8 to 3 for the parallel threads and from 8 to 1 for the concurrent threads. As you can see, it also adjusted the heap regions and the object aging thresholds. As for the previous case, we also got 8 JVM options automatically selected as the most impactful with respect to the dozens and dozens, hundreds actually, of potential JVM options to be considered. All right, this is time to conclude with our takeaways. So our first takeaway is that tuning modern application is a complex problem that is hard to solve. Any traditional tuning approach causes a relevant toil for SREs teams. The second takeaway is that when our new approach is based on a fully automated machine learning-based optimization, it becomes possible for SREs to really ensure that application will have higher performance and reliability. And third, this new approach makes also possible to reduce the operational toils and stay aligned to release milestone. So a huge improvement for all SREs. Many thanks for your time. I hope you enjoyed the talk. Please send me any comment and question by leveraging the SREcon Slack channels or these contacts.